Okay, we're going to conduct a hypothesis test, example 14.1, from beginning to end. And there's a new feature on the calculator you're going to learn about, because we need a way to store tabular data on the calculator, which we've not yet done yet. A study was conducted at the 1% level of significance to determine if there was a relationship between gender and one's view on capital punishment. A random sample of 100 adults was selected and asked their opinion to the question, "Do you believe that the death penalty should be given to those convicted of first-degree murder?" Based on these results, can we conclude that there is a relationship between gender and one's view on capital punishment at alpha equal 1%? So when you read this problem, notice that it's not specifying a mean, it's not specifying a proportion. There's really no words, or rather there's no numbers in the wording of the problem except for the alpha and the sample size. So you'll know that you're using the chi-square test because the problem will also provide you with a table. So when you see that table of data values, you're going to know that you should be using the chi-square test. You've got row classification and a column classification, and you should be conducting a test based on the dependence of the two. So we start with a formulation of the hypotheses. There are no symbols when it comes to hypothesis testing for the chi-square test. The hypothesis for the null hypothesis is going to state that the population classifications are dependent. And the alternative hypothesis is always going to state that the population classifications are dependent. They're always going to take this form. So if we keep that in mind, we're going to formulate our hypotheses using the words the population classifications. That's how we're going to start the phrase of our null and alternative hypotheses. And then we're going to state the two classifications and that they are independent. So remember that independent means no relationship. Our null hypothesis makes the claim that there is no relationship between gender and one's view on capital punishment. And our alternative hypothesis is attempting to prove that there is a relationship between gender and one's view on capital punishment. So for this problem, we're going to say the population classifications, gender, and one's view on capital punishment are independent. And HA, the population classifications, gender, and one's view on capital punishment are dependent. If you don't know exactly what the classifications are from reading the problem, you should jump ahead and look at the table, because the table will be labeled with a column classification and a row classification. So if you look ahead at the table, you'll see on your handout, look on the right-hand side, no, I'm sorry, on the left-hand side where it specifies male and female, it says gender. And then at the top for the columns, it says view on capital punishment. So you can easily come up with the phrasing of the hypotheses by looking at the words used in the table. So here we are. We have the view on capital punishment as the column classification, and we have gender as the row classification. Notice that we have two rows, male and female, for gender. The third row is not counted as part of the data. And we have 1, 2, 3 columns for view on capital punishment, but the last column is not included in the data either. So we have values of 20, 25, 15, 10, 25, 5. Those are the most important pieces of this table. Unlike other sampling distributions, the chi-square distribution does not have a mean. So when asked on your handout, what is the name of the distribution? You are using the chi-square distribution. So it's just an uppercase X. It looks like an uppercase X. It's a Greek letter for chi, and just squared. So chi-square distribution. If we look at the picture of the chi-square distribution, we're going to set up the hypothesis test so that the significant tail on the far right is shaded in with whatever degree of alpha you were given in the problem. All chi-square tests of independence will be one-tailed tests on the right, since a significant Pearson's chi-square test statistic will always be a large positive number. So remember, I had said that when you get a chi-square that's down here near 0, it implies that you have independence, and when you have a chi-square that's up here far away from 0, it implies that you have dependence. So we have this border here, this vertical line, which tells us that if our chi-square is over here in this area, it's far enough away from 0 that we can reject the null hypothesis. And let's remember that in our null hypothesis we stated that we had independence. When we reject that, we're rejecting that there is independence. We're stating therefore that the two classifications will be dependent or related. If the chi-square that we get is less than this wherever this vertical line falls, we fail to reject the null hypothesis. It means that our chi-square is not far enough away from 0, not far enough away to reject the null hypothesis. Now we are going to use p-values again with this test. So ideally, what we want is a p-value for a chi-square that goes to positive infinity. The area continues from that chi-square up to positive infinity, and we want that p-value to be smaller than alpha. Okay, so every time we do a test, we want the p-value to be smaller than alpha. So our decision rule, in this case we were given an alpha of 1%. Is that correct? Yes, alpha was 1%. So our decision rule is going to be to reject HO at alpha equal 1% if the p-value of the sample statistic is less than or equal to 0.01. Okay, so we always want our p-value to be tiny, as small as possible, because a smaller p-value indicates that the chi-square test statistic is far over here, far on the right, far away from 0, far enough to reject the null hypothesis. Okay, we are now going to discover how we analyze tabular data on our calculator. The symbol of the chi-square, the symbol of the sample statistic in this problem is chi-square. So enter that on your handout. We're going to get the value for chi-square using the TI calculator. You can do the same function on the 83 or the 84. Before running the test, we have to put the contingency table into a matrix on the calculator. A matrix is a collection of quantities arranged by rows and columns. We're going to use the views on capital punishment table to build the matrix. So having that table open and then going to your calculator, okay, there's a little the matrix here is in blue above the x to the -1 key. So we're going to hit second matrix, and the matrix menu is similar to the list menu, except matrices are stored like tables with rows and columns and not like singular lists with one column of data. So we're going to move from the names menu over to the edit menu. So use your arrow to the right and go over to edit, and then with edit highlighted and with number 1 highlighted, we're going to hit enter. What we see here are the names of all the different matrices that we can use on this calculator. In this class, I'm going to keep using matrix A to put my data in. So I'm going to be overwriting old problems with a new table every time. If you ever want to store a matrix, you would use a different letter, and you could continue using different letters until you've exhausted the letters. So with A highlighted, I'm going to press enter, and at the top I have a 1 by 1 matrix, which means I have one row and one column. Now that's not what we need here. If we look at our view on capital punishment versus gender matrix, we have 2 rows, male, female, and 3 columns. So I'm going to change this to a 2, and I'm going to use arrow right by 3, and then hit enter. As soon as you hit enter, you'll have all zeros appear in 2 rows and 3 columns. And now you can enter the data. So you hit 20, enter. 25, enter. 15, enter. Enter it exactly as you see it on your handout. 10, enter. 25, enter. 5, enter. Notice that I don't have any columns for row totals or column totals. So be sure that you only enter into the matrix exactly the data that the problem is giving you. So no row totals, no column totals, just the observed frequencies. After that's done, press the stat key, then go over to tests. This is where we conduct all our hypothesis tests. We come down to A. No, it's not. It's C. Okay. C. Chi-square test. So with C highlighted, hit enter. And your calculator will ask you for the location of the observed frequencies. We just put our observed frequencies in matrix A, so I could leave this as is. If I wanted to change this observed frequency matrix to something else, I can go back to the matrix menu. Right now I have to keep the cursor highlighted where it is, but I could go back to the matrix menu, second matrix, and under the names menu I can go down to any matrix I want. So C, for example, and notice that it changed to C. Now, of course I don't want to keep it that way, but if I go back, second matrix, and then press 1 again, it goes back to A. This is where my observed frequencies are. Expected frequencies is basically the calculator is asking you where can the calculator generate the expected frequencies. You can leave this as any other matrix other than A. So if it comes up as B, that's perfectly fine. So you go to calculate, you hit enter, and you get a value for the chi-square test statistic, a value for the p-value, and the degrees of freedom for this problem. The first two are what we want to take note of right now. The chi-square test statistic is 4.513888, etc., and the p-value 0.1047. So we take those that pieces of information, and we have to go and record it. Okay, so we're going to round our chi-square sample statistic to 2 decimal places. So when you are asked to enter the chi-square sample statistic, or basically the value of the sample statistic, that's what the handout says, you're going to write 4.51, and when asked for the p-value, you're going to do what we've always done, 4 decimal places. So the p-value is 0.1047. Now, if we look at what that p-value means, if the p-value is less than alpha, reject the null hypothesis and accept the alternative hypothesis. If the p-value is greater than alpha, fail to reject the null hypothesis. So, in this problem, we have this case. Our p-value is greater than alpha. The meaning of rejecting the null hypothesis means that you found a significant relationship between the population classifications and that they are dependent. And the meaning of failing to reject the null hypothesis means that there's no significant relationship between the population classifications and they are independent. So what this means, p-value is greater than alpha, fail to reject the null hypothesis, it means our classifications are independent. So let's look at the p-value versus alpha. Alpha is 1% and our p-value came out to be a little over 10%. Our p-value is bigger than alpha, which positions the chi-square 4.51 here and not over here, which is what we really needed. We needed our chi-square test statistic to be far away from 0, and it turns out that p-value is too big compared to alpha, so it doesn't position our chi-square far enough away. Can we conclude that there is a relationship between gender and one's view on capital punishment? So think about this for a minute. Did we prove that we have a relationship, or did we prove that we have no relationship? The answer to the question is no. There is no statistically significant relationship between gender and one's view on capital punishment. The two classifications are independent. Okay, so when you have the type of conclusion where you fail to reject the null hypothesis, you're basically stating that the two classifications are independent of one another. So going back to the picture, over here you have independence, and over here you have dependence. If your p-value is bigger than alpha, you have independence. If your p-value is smaller than alpha, you have dependence. Our p-value came out bigger than alpha, so we have independence. Example